we're going to continue on number 5 here, talk about vertical line test in detail. We agree in a rectangular coordinate system, any graph gives a relation because any graph is just a collection of points, right? Maybe finite number of points, or maybe infinitely many, uncountably many points. Either way, a graph in the rectangular coordinate system is a collection of points, and points are ordered number pairs. So any graph is a collection or a set of ordered number pairs. That's the reason any graph in a rectangular coordinate system is a relation. Okay, so here vertical line test is used to determine if a graph a function. We know any graph is a relation, no problem on that. But we want to know if the relation a function, right? Vertical line test is for that purpose. As here it says here, we are going to look at question number 9 in Lumen. Let me go there. I think I have to reshare the reshare the website here. And let me know, do you see my Lumen shop? This is my Lumen system.
Yes.
Okay, cool. In the past, for recent years, I've been using Collaboration Ultra in Blackboard. For some reason, this semester, I do not have the option to use the Collaboration Ultra. I have to use Zoom meetings. I heard that our college is going to stop paying for the Ultra. So in the future, starting from summer, I think, all the classes have to use Zoom meetings. This is just a good exercise. So I'm going to go to number 1.1, section 1.1. Number 9, right? Okay, let's see. What does number 9 says? Question number 9 is to select all the following graphs which represent y as a function of x. In other words, we are given 1, 2, 3, 4, 5, 6 graphs. Those graphs are relations, and we are going to use the vertical line test to determine which of them are also functions. Let's look at the first one. Let me show you how do we use the vertical line test. How does vertical line test work? So you draw vertical lines, okay? I'm not able to, okay, hold on. Let me try this. And you understand what's going on. Then I would have to stop sharing the website and share my OneNote. And share my OneNote. Right here. Nope, it's the wrong one. Okay, this one. All right. So let me show you how do we apply vertical line test. The first graph looks like sines or cosine. This is actually a sine function. So this is the curve. I can make it a thicker. This is the graph. It is a relation. We are going to apply vertical line test. We're going to draw a vertical line. Do you see any vertical line exist that would cross the graph more than once? The curve going down and going up and going down and going up?
No.
Do you agree? You're right. There isn't such a vertical line possibly cross the graph more than once. It doesn't exist. If this happens, we say the graph passes the vertical line test. If the graph passes the vertical line test, then we say the graph is a function. So this is a function. Some of you might remember this is the sine function, right? The second one, the one on the right, the circle. This is the graph. It is a relation. Can we find a vertical line that crosses the graph more than once?
Yes.
Very obvious, right? The vertical line test is a very easy technique to grasp. As you can see, this vertical line crossed the graph more than once, exactly twice. And let's say this point is 4 comma or x comma y1, and this point is x comma y2. So you can see those 2 points, since they are vertical aligned, they have the same x value, but they have different y value. So we have a cheating husband here. X here have 2 different y's, make a pair with it. If that happens, we say the graph fails the vertical line test. Then the graph is not a function. Does that make sense, guys? I think this is a pretty
Yes.
doable technique, vertical line test. Then let's go back, Lumen. Lumen is here. And we agree the first graph is a function, right? And the circle is not, because easily we can find a vertical line cross the graph more than once. What about this one? This is a horizontal straight line. Is this a function or not? Use the word. Yes, it is, right? It's actually a constant function. You will not have any vertical line cross this horizontal line more than once. So it is a function. It is a constant function, by the way, constant function. And what about this slant straight line? This is slant straight line. Does this pass the vertical line test? Is it possible we can find a vertical line, draw a vertical line, cross the graph more than once?
No.
No. Yeah, it passes. It is a function, right? Obviously, this is a linear function. It is a linear function. Next, this actually is a polynomial function with degree 3, but you don't have to know that. Maybe in the later chapters, but at this point, it doesn't matter. This is a graph in the rectangular coordinate system. It is a relation. Let's use the vertical line test to determine if this relation a function. Pass or fail. Is there a vertical line pass the graph more than once? What do you think? This is a function, okay? You will not be able to find a vertical line cross the graph more than once, because it goes up, goes down, goes up. It doesn't, like the circle, like doesn't go back. In each interval in a domain, there's only either goes up or goes down. But in this circle, for a part of the domain, is go up and go down, right? Go up and go down. The last one, what do you think about this graph? Is this graph a function or not?
No.
No, you're right. Yeah, we can draw a vertical line like this one, cross the graph 1, 2, 3, 3 times, fail the vertical line test. It is not a function. All right, so let's submit this question. What does the system say? You can retry this question below.
I think you accidentally selected the one that
Accidentally, oh, oh yeah, you're right. And then do that again. It fixed, right? And I recommend you can try here, get a similar question. Then you have more practice. Let's go to next question, number 10. this one is not. Let's go back my lumen. Okay, so that's vertical line test. I think we are clear on that. Next one, summarize the ways to describe a function. Okay, so there are multiple ways to describe a function. I'm going to introduce the way I think is the best way to understand a function. I understand function as a machine. The machine produces exactly one outcome, output for any given input. So this is the way I want to show you how to understand a function. Let's go back number 2. The first example is the names, person, and their eye colors, right? We agree this is a function. It is a relation, also a function. I'm going to describe this function as a machine. This is a machine. We can describe this function as a machine. Whenever you give the machine an input, the machine will only produce exactly one corresponding output. Input here is the value of x. Output here is the value of y, right? Or the first component in the pairs of the function, they are inputs. The second components, they are outputs. The domain give all the inputs. The range give all the outputs. So this machine, input are the names of the people or subjects. Outputs are their eye color. So I invented a machine, very cool. If you type the name of some person, and the eye color will come out, right? Somehow it's programmed. So if I tell the machine, tell me what's the eye color for Alice, and the machine will tell me Alice's eye color is brown. If I give the machine input Bobby, the corresponding output is blue. That means Bobby's eye color is blue. If I tell the machine, now I'm going to give you the input Cindy, then the machine will produce the corresponding output green, and that's the eye color of Cindy. If I give the input as Danny, then the color of Hazel will come out as the output. As you can see, for any given input in the domain, this is our domain, okay? Not Betty, my name is not there, so I'm not a domain element. Only those 4 people in the domain. For any domain element, which we call input, the machine only produces one exactly corresponding output. Then this is a function, okay? So I can show you for the first domain element, Alice, we got a brown eyes, right? One output only. For Bobby, we have the blue eyes, one output as well. For Cindy, that's the third domain element. We have green, only one color, one output. For Danny, one color only, hazel. So if you have something that you can describe that as a machine which only produce exactly one corresponding output for any given input, then the thing is a function, okay? It's a little bit abstract. It could be anything, right? You can actually see the input as a Barbie doll, and then the machine programmed to put a shirt or dress on the Barbie doll. So the corresponding output would be a dressed up Barbie doll, right? Something like that. The second example, we agree it is a relation, but it is not a function, right? Because we identify a cheating husband. So if we want to describe this relation as a machine, let's see what happened. This relation has 3 domain elements. The 3 domain elements are 1, 2, 3, right? Let's see what happened to those 3 domain elements. If I give the machine the first domain element 1, the corresponding output is -1, right? Because 1 corresponding to -1, 1 comma -1. If I give the machine a second domain element, which is 2, and I will have a 0 as the corresponding output, right? Yeah, this arrow hat go from 2 to 0. But if I give the machine the third domain element 3, and the machine will produce two different outcomes, or outputs, two different outputs. One is 0, the other is 1. Do you see that? So this machine is not a function because this machine produces two different outputs for the given input 3. That broke the
I
deal.
don't know what, I'm sorry, but I'm still just seeing the homework 1.1 functions. Am I on is this something else that we're looking at right now? Or are we still just,
Am I sharing?
it's just still,
Notes?
it's still on the Lumen, so I can't, I don't
Oh,
know if it's,
am I
I can't see
don't,
anything.
okay, because I was like, am I losing? I just wonder if
Let's,
the computer
yeah,
froze.
I'm sharing my notes now. I'm gonna try again.
Yes, now I can see them. It was
Okay,
still
cool.
on the Lumen.
Oh, maybe I messed it up. Sorry about that.
Right now,
Yeah, that's why I prefer Ultra better. Okay, let me redo this part. So this example gives a relation, but the relation is not a function. Remember, we identify cheating husband, right? 3 is the cheating husband. And I use a different perspective to show it is not a function. Because if we describe this relation as a machine, the machine will produce two different outputs for the given input 3. When you give the input 3, two different outputs will come out as a result. So that broke the deal. So this relation is not a function. To be a function for any given domain element, for every single x, for every single input, the machine can only produce exactly one corresponding output. Please let me know, do you like this way to describe a function? It's actually pretty helpful, this way to describe a function.
Yeah, it makes a lot of sense.
Perfect. Then I'm gonna continue, all right? Yeah. Number 3, here we agree this relation, yeah, definitely is a relation, but it's not a function because we identify a cheating husband, which is 1, right? So if we describe this relation as a machine, let's see what does the machine do to those domain elements. We have 3 domain elements. D here is the domain, right? Domain has 1, 3, 5, 3 elements in it. If we give the machine input 1, so we would have 2 different outputs, right? 2 and -2. So we don't even have to continue. It doesn't matter. The machine produces 1 output for input 3, 1 output for input 5, but for input 1, the machine produced 2 different outputs. So that ruined the chance for the relation to be a function, right? Yeah, you also can see the input is the husband. It has 2 different families, it doesn't function, right? It doesn't function. So this is not a function. And next one, similarly, I can show you the way to describe this function as a machine. So we agree this is a function because this graph passes the vertical line test. And then let me show you how do we describe this function as a machine. So when you give the machine input, we have how many inputs? We have 1, 2, 3, 4, 5. 5 domain elements. So for each of them, I'm gonna draw 5 machines. It's the same machine, but I use it 5 times. 2, 3, 4, 5. When you give the input 94, can you tell me what's the output? What's the output corresponding to input 94? Output is Y, input is X. My question was, I'm going to describe this relation as a function. Let's see what does the machine do as a machine. Let's see what does the machine do to each single domain element. We see the domain elements as inputs. If we give the machine input -4, what is the corresponding output? Guys?
4.
4.
4.
Positive 4, okay. Yeah, I should have scrolled down a little bit, right? It was covered earlier. Very good. Help me out. Continue, help me out. Here, if I give the machine input -2, what's the output?
2.
2.
2.
Okay. One output only, right? If I give the machine the third domain element is 0, and what's the output?
0.
0.
0. If the input is 2 positive, what's the output?
2.
2.
If the input is positive 4, what's the output?
4.
4.
Perfect. Perfect. As you can see, this machine produce only one corresponding output for any given input in the domain, right? It is a function. It is a function. Okay, continue using this idea, using this perspective to understand function. And this graph is a linear function. We agree. It passes the vertical line test. The equation corresponding to the straight line is y equals x plus 1. If you have a memory from Algebra Foundation 2, this is a slope-intercept form of the function, right? Of the linear function here. How do we describe this linear function as a machine? How does that work? Okay, so whenever you give the machine represent this straight line. Whenever you give the machine an input, again, the input is a value in the domain. The machine will produce exactly one output because the output is always equal to the input plus 1. This equation determines this relation, this graph is a function because x represents the input, y represents the output, the corresponding output. So whenever you give the machine an input, the corresponding output is always one more than the given input. For example, if you give the machine 100, what's the output, guys?
100.
101.
Exactly, right? You will not have two different wives. I mean, you will not have two different corresponding outputs for 100 because you just need to add 1 on top of the input, right? Yeah, for this function, the output always equal to input plus 1. So whenever you give the machine an input, the output would be just the input plus 1. So the machine will not produce two different output for any given input. For that reason, this machine is a function, right? So input output is x, output is y. Very important. For this function, the output is always one more than the input. Very good. This parabola is more tricky. The relation, the equation describe partial part of the parabola is y equals x squared. Okay, the domain is not all real. Is any numbers bigger than 93? So how do we describe this graph as a function? It is a function because it passes the vertical line test, right? You can see that probably very easily. It passed the vertical line test. There's no vertical line test. A vertical line would pass the graph more than once. Okay, this is how we describe this function as a machine. Whenever you give the machine an input, the output is just the square of the input. Okay, it's exactly what the equation shows. X is the input, y is the output. How does this function, this machine work? Whenever you give the machine input, the corresponding output would be the square of the input. Okay, so if I give the machine input 5, can you tell me the corresponding output?
25.
Exactly. What I just said basically is if I give x 5, then the corresponding y value is 25. And also for any function, as you can see, since it has two components, right? First components, they are values of variable x, and we can use x here as a variable to represent all the values in the domain, and use variable y to represent all the values in the range. And those two variables have played different roles. Again, variable x is the husband, variable y is the wife. They play different role in the family. Wife depends on husband. Let's say it's the old time. Once the women get married, they don't work. Financially, they depend on their husbands, right? So wife depends on husband. Variable y depends on variable x. Output, y is output, x input. Output depends on input. Okay, you feed the machine input first, and then the machine produce a corresponding output. Not the other way around, okay? X is the input, go first, and then Y is the corresponding value of the function. Okay, let's see on my note. So that's the way to, there are other description, but I'm not going to talk too much about it. And today we're supposed to finish section 1.2 as well, so we are already a little behind. So here we describe a function as a machine. The machine produce exactly one output for any given input. So just understand function like that, all right? So next up, we are going to talk about the notation of function. You might see f of x, you might see g of x, sometimes you might even see h of x. And what is that? That's the way we denote functions. Okay, most of the time is f, because f is the initial function, right? Let's say we use f. The time we use g is because we need two different functions, so we cannot use f for two different functions, so we use g. So let's take a f of x as an example, and you need to remember f of x is just a y. F of x is just a y. Okay, this equation represents a function if x here, the husband, represent all the inputs in the domain, y here, the wife, represents all the outputs in the range. And for any given husband, there's only one corresponding wife. So if this equation satisfies that condition, this is a function. And I think the useful information you need to know about this is the right side f of x. You can understand this as an expression in terms of x. For example, earlier, our straight line y equals x plus 1. This is a function, right? Y equals f of x. F of x here is x plus 1, right? X plus 1 or f of x here is an expression in terms of x. You can also see f here as the machine, as the operation, right? As the machine. When you give the machine input, means you put the input in the parentheses, and the machine will apply the programming, some treatment, and the output y coming out. I can give you a fun example if you hope you like it. For example, you give the machine, this is the machine f, okay? This is the function. If you give the machine the input pig, a hog, the output is pork. You give the machine a cow, and the machine produce beef. You give the machine chicken, and the machine produce chicken. It's just the meat of the animal. You can see the f here as a mapping or an operation or a certain treatment. you know? Okay, so one important thing you want to know is f of x here is an expression in terms of x. And the parentheses right next to f, in the parentheses, we always have the input, okay? The input always go in the parentheses, go in the parentheses, go in here, that's the input. Okay, I think the best way to explain what I'm trying to tell you here is to look at the example, all right? Let's look at example 7. Let's say we have two different functions, so we need a different ladder. Besides f of x, we also have gx. F of x, as you can see, is an expression in terms of x, right? It is 2x minus 3. You can also see this equation as y. Remember, f of x is just y. Y equals 2x minus 3. So this is the function y equals 2x minus 3. It's just we use f of x to represent it. And the second function is, I'm going to erase those to have more space. G of x here is also y. Guys, g of x here is also y. Is the output. Output y equals x squared. So this equation represents function g. G of x is just a notation for this quadratic function, degree 2. Okay, so now we know the two functions. One is f, the other is g. Let's complete the following 7 parts. The first part, we need to look for f of 5. Once you understand the notation, I believe you know how to find the answer. Remember, I say the stuff in the parentheses next to the function name f is always the input. So this means the output of a function f when the input is 5. Okay? This notation means the output of the function f when the input is 5. So in other words, you see this is about the function f, right? In the parentheses, we have 5. So the input is 5. What's the output of function f when the input is 5, guys?
7.
How do you get a 7?
2 times 5 is 10, minus 3 is 7.
Yeah. So you might think, I do not need to think about that much. I know how to do that. I just need to plug in x equals 5, right? Perfect. That's one way to do it. But it's good. Ideally, I hope you see the input-output stuff, the relation here. So 2 times 5 is 10. 10 minus 3 is 7. Awesome. The corresponding output is 7, right? Number 2, we are looking for g of -3. The parentheses follow g, so we are talking about function g. So the second function, then it has nothing to do with a. Okay, awesome, very good. So this means the output of the function g, the machine g, when the input is -3. So when you give the machine g -3, so how does the function g work? The output is always equal to the square of input, right? So when you have the input -3, then the output would be square of the input, and that gives 9. Perfect. In other words, you can just plug in, especially when the input is just a one specific value. You really could just plug in to make it very simple. Number 3, we are looking for f of t. How do we find f of t? We do know the value of t. T here is just an input in the domain. Since it is f of t, it has nothing to do with g, so we're gonna look at f of x only. How does f of x, this function work, this machine works? When you give the input, the corresponding output is always double the input and then subtract 3, right? That's how the machine works. Would you try to find the result for f of t? Function f, machine f, when you give the input t, what's the output? You can also try just to plugging in x equals t.
It's 2t minus 3.
Exactly. Perfect. The output will involve t in it, right? Because the output depends on the input. The input is t, the output for function f is twice of the input and then minus 3. Is that clear, everybody? Is that doable?
Yeah, it's clear.
Okay, very good. Thank you for your response. Okay, so number 4. Number 4, we need to find g of x plus 1. Can you tell me what's the input in number 4? What's the input here? Is the input x or 1 or something different?
X plus 1 is the input.
Exactly. The whole thing in the parentheses, that's the input. That's the input. So this notation means the output of function g, of machine g, when the input is x plus 1, right? Let's see how does the machine g work. Let's see. Machine g is g of x equals x squared. So the output is always equal to square of input. That's the programming of machine g, right? So when your input for machine g is x plus 1, the whole thing, the whole expression, x plus 1, what's the output?
X plus 1 squared.
Do you mean this?
Yeah.
Perfect. Yeah, you do not have to distribute, okay? You do not have to use a FOIL. That's good enough. Actually, I prefer you keep that like that. Perfect. And number 5, we are looking for f of g of x. For this time we have this notation quite a little bit more complicated, right? This notation involves f, also involves g. What does that even mean? You don't have to overthink. How about let me color whatever inside the parentheses next to f in blue. So do you agree? This is about function f. And the input I give function f or machine f is the blue. Do you agree that?
Yeah.
Yes.
Yeah.
Perfect. So the function f, let's see the machine f. What's the relationship between output and input? For function f, the output is always equal to double the input and then minus 3. Do you see that? Every function is different. Every machine is different. For this specific function, it is given f of x equals 2x minus 3. For that function, the output always equal to twice of input and then subtract number 3. So in this case, number 5, our input for machine f is blue. That's the input, the blue. So the corresponding output would be double the blue, because blue is the input, right? Double the input and then minus number 3. And what is blue? Blue is g of x, right? And what is g of x? Do we know what is g of
X
x?
squared.
Squared.
Yeah, it's given right here, x squared. So it is 2x squared minus 3, and that's it. Let me know if you see it. I really think it's important to see this. A function is a machine. Every function, of course, is different. Every function is unique. It has its unique programming. The programming determines how the output depends on the input. For function f here, output is always equal to twice of the input and minus 3. If you give the input, if you give the machine, let's say the input is a Barbie doll. I know Barbie doll is not a real number. Suppose it's in the domain. Then the output would be twice of the Barbie doll minus 3. Let's say the function g. The machine g has output always equal to square of the input. If you give the machine g a pencil, the machine g will produce square of the pencil. That's the programming of that function. Let's try number 6. Let me scroll down. I also need to show the two functions. Number 6. Next time I need to leave more space on this file. Number 6 is g f of x. This notation also involves both functions f and g, but we mainly concern the one on the outside, okay? Because the inside, let me change a different color. Let's use green this time. This f of x is inside the parentheses next to g, so I highlighted in green, and that green is just the input for function g. Okay, remember how does the function g work? You give the input, you give an input to function g, the function produce square of the input. For function g, the output always equal to square of the input. So do you agree the result is supposed to be square of the green? Because the green is the input, right? So the output would be square of the input. And what's the input? The input is f of x. What is f of x? F of x is 2x minus 3, and that's it. Please let me know, is that understandable?
Yeah, I understand.
Perfect.
Yes.
Awesome. Thank you for your response. And number 7.
So is it just because it's the square? Oh, the 2 is, oh, okay, never mind. I was just having a minute about where the 2 was coming from, but it's in the expression.
Yeah, the square is determined by the programming of machine G. Machine G always produce the output as the square of any given input because it says g of x equals x squared, right? So as you can see here, this is the input, this is the input, x is the input,
Okay.
and the output would be put a square on the shoulder of the input. Okay, the last one, the last one is about function f. When you solve f of x equals 13 for x. So earlier, those parts in the problem, we are given input and we are looking for the corresponding output, right? Here is different. Here, number 7 is we are given the output. So we know the function f now just produce an output, output 13. And we want to know what did you give the machine? What's the input you give the machine that the machine produces 13 as an output. So
23.
let's see how do we handle that. Let me see if I can get more space here. Yeah, number 7. So we know f of x equals 13, means the output is 13. We want to know what's the input. Well, you don't have to struggle too much. F of x is given as 2x minus 3. We can just solve the equation, right? And just solve the equation.
8.
Yes, I agree. Yeah. So you add a 3 to both sides. You cancel those 2. You have 2x equals 16. And you divide each side by 2. you have x equals 8. You're right. Only when you give the machine input 8, the corresponding output is 13. If you're gonna give the machine other input, the output would not be 13. Sometimes we do the other way around. Most of the time, you are given the input, you need to find the corresponding output. Sometimes the question wants you to find the value of input for a specific output. I hope after we have more to practice here. We have 2 more questions to practice here. Number 7, number 8. Number 7, number 8. Let's go to 1.1. Number 7. Below is the graph of function g of t. Estimate as close as possible the value of g of 2. We need to understand this notation, right? Do you see the lumen? I probably have to switch again. Switch back to lumen. I was on my note, so now we are going to go back the browser here. All right. Below is the graph of a function g of t. Estimate as close as possible the value of g of 2. We need to understand the notation here, g of 2. Do you agree the 2 here is the input? Remember, input is x, right? X is a horizontal scale. The input is on the horizontal scale. Output is on the vertical scale. So basically here, we are looking for the output for function for this graph when the input is 2. In other words, when the first component is 2, when x is 2, what is the corresponding y? Let's see. 2 is here, right? And what is the corresponding y?
-3.
Yeah, I would say -3 is the closest. Do you guys agree? -3?
I agree.
Perfect. Feel free to let me know if anything is not clear. Any questions are good questions. Any questions are appreciated. If you don't let me know, I will not be able to know. I don't see you. If I don't hear you either, it's really hard for me to accommodate your need. Very good. That's number 7. Pretty simple problem. Number 8. This also has a graph. The plot below represents the function f of x. Solve f of x equals 4. Okay, I have a question. Is 4 here input or output? Is 4 here value of x or value of y?
Y.
Yes, you're right. Perfect. Output y. Remember, y is on the vertical scale. So I think 4 is here. On a vertical scale, 4 is here. And what's the corresponding x?
3.6.
Negative. My
2.
92, right? Yeah.
Mm-hmm.
Very good. And that's it. Pretty straightforward. And let me go back my note. I need to stop share and share my note. My note. Is it note? No. Okay. All right. We finished section 1.1 now. I hope you have a a lot of better understanding about what is a function, especially the way we describe a function as a machine that produces a unique output for any given input. And that's a very useful, very helpful way to understand function and process any problems about functions. Functions are just the input output, right? Every function is different, of course. A specific function has its unique programming. It determines there's a certain way to produce the output for any given input. Okay, now we are going to continue to talk about section 1.2. Section 1.2 only have two things, pretty simple. If we don't finish all of them, I think next time we only need to spend a little bit of time to finish 1.2, so it's not a big concern. The first thing in section 1.2 is rate of change. Average rate of change. Let me give you the definition. Let's say function, let's say f of x is a function. A comma b. This is a interval. This is an interval. This is a closed interval. You should have learned closed interval in algebra 2. So this is the real number line. If this is A, this is B. Closed interval is this interval including both endpoints. So let's say that interval is in the domain. Is in the domain. We define the average rate of change of a function f of x over the interval AB is defined as f of b minus f of a all over b minus a. This is the formula for the average rate of change. Average rate of change. Let me give you an example to understand what's going on here. Let's see if this example could help you on this formula. This obviously very abstract, right? So let's say you have a son, you have a teenager son. In the past 5 years, right now it's 2025, so it's gonna be 2020 to 2025. So in the past 5 years, your son has grown from so let's say in 2020 he was 3 feet, but by the year of 2025 he have grown to 6 feet. You see that? So over the 5 years, he has grown 3 feet, right? Then what's his average rate of change? What's his average yearly growth? From 2020 to 2025, the total growth is 3 feet, right? 3 feet to 6 feet, the difference is 3 feet. And if you use 3 feet to divide by 5 years, then the average yearly growth for your son would be 3 divided by 5 is 0.6 feet. Does that make sense, guys?
Yes.
Okay. And Here, X, the independent variable. By the way, X here, husband is independent. Okay, they make their own money. Y, here's a wife, so it's a dependent variable. So in this case, the independent variable is time. When the time goes from 2020 to 2025, your son's height, which is Y, in dependent variable, goes from 3 feet to 6 feet, right? So we just need to use 6 feet minus 3 feet divided by 2025 minus 2020. That example provides an idea about how do we understand average rate of change. Your son's average yearly growth over the 5 years, that is an example of average rate of change. And it's good to know the formula, but mainly we want to know the meaning, right? So what is this meaning means? It means this actually f of b is the y value when x equals b, right? And this actually is the y value when x equals a. In other words, a is input because a is in the domain. F of a is the corresponding output. B is an input. F of b is the corresponding output. So when the input change values from A to B, it basically means when the input change values from A to B, then the output would correspondingly change the value from f of A to f of B, right? So they want to know the average rate of change of f of the output. So you just need to use the difference between f of A, f of B to minus difference between A and B. You might remember in let's see if I graph a straight line here. If I graph a straight line here, and this is A, this is B, right? And this would be f of A. And let's say the function f of x represents a straight line. Then this is the f of B. F of B minus f of A, this part, that actually is our rise. Do you agree that's the rise? And B minus A from A to B, that's our run. And the average rate of change is actually rise over run, is the slope of the straight line. Do you see that as well?
Yes.
Yeah, I give you 2 examples, just want you to connect this new formula with something familiar, more familiar with you. Okay, let's look at examples. We plan to cover 4 examples. Let's look at number 7 first. Let me see if I can copy paste number 7. Well, now I'm gonna go back to Lumen. And look for 1.2. In 1.2, I want to look at question number 7 first. Question number 7.
It's still on your notes.
Yeah, I'm going to copy paste. Then I don't have to switch share back and forth, very troublesome. We're gonna copy paste here. Bear with me. Number 7. This is number 7. Do you see the thing I just pasted?
Yes.
Okay, awesome. This is number 7 in Lumen 1.2. Let's read the problem. Find the average rate of change. Well, you do need to know the name, right? It's like when you meet a friend, isn't that important to know the friend's name? The next time when you see him or her, you know how to say hi, right? Same thing, in section 1.2, we learn a new content. The name of the new content is the average rate of change of a function. Is about function. And the formula to compute the average rate of change of function is this. And by the way, when we talk about average rate of change, we have to consider the whole package. It doesn't mean anything when we just say average rate of change. Average rate of change. We have to say average rate of change of which function over which interval is a whole package. Missing any part, the concept doesn't make any sense. So in this case, we are looking for the average rate of change of this function. It is given f of x, right? This function. On what interval? Over this interval from 93 to 92. Okay? So let's process this problem. F of x is given, and the average rate of change of the function over interval AB is f of b minus f of a all over b minus a, right? So in our example, a is 93, is the starting point of the interval. B is 92, is the ending point of the interval. So we have a and b found. Then what is f of a? What is f of b? Okay, so f of x equals 6 over 93x plus 3. This is how does machine F works. When the input is x, the output, the corresponding output is 6 over 93 times the input and then plus 3. And with this given, can we find the value for f of 93? A is 93. Based on the formula, we need to know f of a, right? So we need to find the f of a. F of a is f of 93. How do we find f of 93? Let's plug it in. Numerator 6, denominator, the input is 93, right? So put it here. Sometime in algebra class, I would make my students do this. The function is 6 over 93x plus 3. Whenever you plug it in, you firstly use a parenthesis to frame the variable. And you get rid of the variable. And then you put the value you're going to plug in the parentheses. And since this is a pre-cal, I believe you probably know this very well. So I might not go that detail. And then 93 times 93 plus 3. Let's see what we have. Numerator is still 6. Denominator, negative 3 times 93 is a positive 9. Add 3 is 12. 6 over 12 is a half. So that's how do we find the value for f of a. I'm going to give you 1 minute. Please help me to find the value for f of b. B here is 92. So you are going to plug in x equals 92 to find the corresponding output. I'll give you 1 minute.
Two-thirds.
2/3. I agree. I think is correct. 6 on the top, 93 times 92, and then plus 3 on the bottom. 93 times 92 is a positive 6. 6 plus 3 is 9. 6 and 9 have a common factor 3. Divided by 3, divided by 3. We have 2/3. Perfect. Very good. Now that we have all the components, all the pieces in the formula, we have all the pieces in the formula. A, which is the left end point of the interval, 93. B, right end point of the interval, 92. F of A, half. F of B, 2/3. All the 4 things we found, now we can plug it in, right? So f of b, 2/3, minus f of a, 1/2, all over b, 92, minus a, 93. Be very careful. We will need to minus a negative number. You must use a parenthesis to frame the negative number. Otherwise, it's very likely to make a mistake. All right, let's simplify. I can simplify the denominator. 92 minus 93 is plus positive 3, so it's 1, right? And another way to quickly find out the denominator, remember the interval is on the x-axis. This is 0, this is -1, -2, -3. So the interval is a part of the horizontal scale. In this case, we have a left endpoint 93, that is A. We have a right endpoint 92, that is B. The denominator of the formula basically is the distance between A and B. In other words, is the length of the interval. If finding length is easier than doing minus negative things, sometimes people do mess up this part. And just look at the graph of A and B on the x-axis. So the distance between A and B is 1, right? The length of the interval is just 1, so we know it's just 1. And the numerator, 2/3 minus 1/2. The common denominator is 6, so we multiply 2, here multiply 3. In the syllabus, I said that you can take any calculator with you. So if your calculator can do fraction, that's fine, because fraction is not the focus of pre-calc. And now we have 4/6 minus 3/6, and that gives us 1/6. 1/6 divided by 1 is still 1/6. So the answer is supposed to be 1/6 for number 7. If I go back and enter 1/, and have to stop share. Let me look at the share option. Share this. In the past, I know the Zoom doesn't have an option to share the whole desk. So I need to switch from this app to the other app. I'm not sure if they improved on that, but I don't find that option here. So now let's share Lumen. I enter my answer 1/6. This is for you to figure it out. It's pretty cool. It's a fraction, so we want to use this structure, right? So numerator is 1, denominator is 6. Sum it. Is that correct? Yeah, it is correct. Does that make sense, everybody? And now let me stop share this one and share my notes here. Any question about number 7? Rate of change, average rate of change.
No.
Awesome. Thank you. I want to emphasize in the formula, the denominator is a change in the input. The numerator is a change in the output. And we know output depends on the input. And the change in output is caused by the change in the input. Just like the example I gave you, the growth in your son, the growth in your son's height is caused by time, over time, right? So the denominator would be how long, how many years, and the numerator would be time in years, right? From 2020 to 2025. So did I say 2025? We just start 2025, right? Well, it's a convenient number. Let's just pretend it's okay. And the numerator is the change in his height. He was 3 feet, now it's 6 feet. So the change in his height is 3 feet. So this is the quotient here. Rate of change. Rate here means the quotient, right? Yeah, what is the rate? Rate means quotient. Change means the formula, actually the average rate of change is the quotient of the change in the output over the change in the input. Because output depends on the input, when the input changes, the output would make corresponding change. And the average rate of change describe, averagely speaking, every time when the input change 1 unit, how much change it causes in the output. So that's how we understand the meaning. I don't really want you just to know how to plug in the formula. I want you to really understand the meaning of average rate of change. I hope I can make that happen. It's okay, we just started this topic, right? Next problem, we are going to look at, this is number 7. We're going to look at number 3 in Lumen. Bear with me, I'm going to do the same thing. I'm going to copy paste. I'm going to get rid of this problem to the next page and get a blank page. I'm going to share now question number 3. Number 3. Find the average rate of change of function g. Different function, right? Function g here is linear, is -3x minus 4. Between the points -2, and 4, -16. So this problem asking about the average rate of change by giving you different type of information. The previous problem, they just give you the interval, right? They give the interval. Then it's more convenient if you have the interval, it's more convenient to apply the formula if you know what's the interval. But here it doesn't. This question does not tell you which interval. You have to figure it out. Okay. Knowing the interval has to be part of the domain. Okay. So look at those two pairs that is given. 92,2 and then 4, -16. So this is x, this is y. This is x, this is y, right? So we have two different values. We have two inputs. We have two inputs, 92 and 4. Okay, so on the x-axis have our inputs. So the two inputs are 92 and 4. 1, 0, 1, 2, 3, 4. So this is the interval. This is the interval. Okay, so now we found our interval. We know this is A, this is B. Correct? But to apply the formula f of b minus f of a all over b minus a, we need to know f of b we need to know f of a, right? But you know what? You don't really need to use this function. You don't need to use that function because the corresponding output for A is 2. Just look at the pair. This pair gives us the output when the input is -2, right? So basically, the -2 is A, and the 2 is f of A. The output is 2. We already know that. And here, 4 is the B, -16, the corresponding second component, is the output, f of B. Do you see that, guys? Do you see it?
A little bit, if I'm being honest.
So if we, how about, let me graph the straight line here.
So I guess if this is a linear,
Yeah, linear. 1,
okay,
2,
so
3.
I guess can't you just use the slope equation to find
You're
the...
right. It's actually just this, it is the slope. You're right, it is the slope. It is the slope. It is just the slope.
So
So
is it -3 or no, that's not right. Okay, sorry. Y equals mx plus b.
we'll go down 1, 2, 3. So this is a straight line. This is a straight line. So one point is -2, comma 2. So we have 2 points on the line. And this actually is just the slope in the slope. Rate of change, average rate of change for a straight line is just the slope. I was trying to show you that how do you find the pieces in a formula, then you can just plug it in. Okay, how about this? We do one step at a time. Do you agree B is 4?
Yes.
Do you agree A is -2?
Yeah.
Because we have 2 pairs, that means we have 2 inputs. We have 2 values for x, 2 domain elements. One is -2, the other is 4. And the reason we put a 4 first because it's bigger, right? It's bigger. -2 is to the left of +4. So we use B minus A. So I was trying to explain how do we know, or how do we find f of A? How do we find the f of A? What I'm trying, sorry, G of A. Sorry about that, G of A. We don't have f here, G of A. We do not need to plug in to find the G of A. If you plug in, let's see what we have. We don't need to, by the way. If you really spend time to plug in, 93 times A is 92. 93 times 92 is +6 minus 4 is 2, right? And it's already given, is right here. The output is already given. Input and output make a pair, right? I was trying to explain the second component in a pair is f of A. And the second component in this pair is f of B. So we plug in the formula, f of B is -16 minus f of A is 2. It is really the same with the slope formula. Is that better?
Yes, yeah, that's more, I think, easy to use that one.
Yeah.
But it only works for linear, right?
Yeah, we do not need to plug in. We don't have to go through that trouble. In a pair, 92 is the input, 2 is the corresponding output. 4 here is the input, -16 is the corresponding output. If we let 92 be A, then 2 would be f of A. Then 4 is B, -16 is f of B. So you can just plug in the 4 pieces in a formula and then calculate. So here, -16 minus 2, -18. 4 minus -2 is 4 plus 2, which is 6. It's -3, right? And it's the same with the slope. It is -3. If you already see, some of you know average rate of change, because the rate of change for a straight line is steady, is a constant. Is it not just the slope? Yes, it's just -3. In the future, if you see a linear function that we need to find the rate of change, it is just the slope -3. Then we don't have to go through all the troubles. I did more than we need for this specific question, but I just want to show you the connection.